So hey, it's great being here. Nice to meet you. My name is Shimon Ben David. I'm the Chief Technology Officer of a company called Weka. For sure, everybody's familiar with us, right? Show of hands. Great. All the hands are up. Great. So I'm here to talk about a very important topic, about memory-first architectures for agentic AI workloads. I know that's a mouthful, but it's a very important topic as you're going to take your inference environments to production. So we are in the age of agentic AI, right? What does that mean? Running models, running code, running software that is going to be an integral part of our workforce, performing operations that we would have performed for us. And we're going to talk more about it. If we're looking at AI workloads throughout the years, throughout the phases, obviously we started many, many years ago with massive AI ML environments, training environments, feeding data to models, building the models, all of these notions of AI, of data as code, right? The more data you have, the more your models would have been accurate or are accurate. Then we moved on few years ago to large language models, right? The ChatGPT environments where models have been created and could generate data with little context. Moving on to reasoning where you're not just generating the next letter, the next word, you're actually models that are generating the next words, then doubting themselves, taking a better decision, right? And providing a better answer. All the way to agentic workloads, agents, as I mentioned, taking information, reasoning around it, and then performing a task, right? Just a show of hands, who's running any training environments? Great, small number. Who's running any LLMs in their environments or playing with LLMs? Great, also some show of hands. So I want to ask about reasoning and agentic workloads. Maybe I will ask, who's planning to implement any sort of AI strategy in their organization? Great, some show of hands. So I hope we're in a good conference here. So if we are looking at, or maybe I'll say another word here, training, just to make it obvious, training is generating the models, whether it's classical AI ML. Inferencing is running these models at scale, or in the purpose of running it at scale. If we're looking at the environments that we're seeing today, trainings are actually, it's a certain environment, right? It's very GPU utilization. I'm feeding data to the GPUs. They need to train the model, create the vectors, create the tensors. So high GPU utilization to maximize throughput. It's very long batch operations. We're working with organizations that are running training for hours, days, weeks, right? It's very much an HPC environment, right? You're throwing jobs, a batch operation, and the job completes in a few weeks. All of the notions around checkpointing the environment, recovering from checkpointing, right? These are the requirements of training environments. Inferencing, on the other hand, which is, I think, what the majority of organizations are going to move to, obviously. Inferencing, I don't need to train a model. Maybe I downloaded some models from Hugging Face or from a different model repository. Maybe I trained a model, but I'm running it in production. Inferencing is completely different in terms of requirement. Inferencing is a very low latency, real-time environment. Think about it. If your kid or your employee is now running a query against ChatGPT or your corporate workload or your corporate AI workloads, if it takes a second or if it takes a minute, that's a completely different experience, right? So these environments, these inferencing environments are completely different than training. They're real-time, they're bursty because, employees are working at different hours of the day, asking for different amounts of data. So they're not sustained. You could have a peak of inference and then a drop. And what we're seeing is, as you deploy inference environment at scale, obviously you're bringing up massive GPU environments or accelerator environments. You're throwing more GPU cycles, more GPU memory. All of these GPUs have a memory within them. You're throwing that on the environment, and all of the prompts are going into your GPUs and asking for information. As you scale in a production-grade environment, not when you're running on your laptop or 1 or 2 POC environments, but in a production environment at scale, in order to get value from your AI, compute alone doesn't solve your scaling problem, right? That's important. Throwing more GPUs in order to accommodate for more users doesn't necessarily solve your problem in an economical way, because eventually your inference challenge, if you look down right into how it works, your inference is bottlenecked on the memory of the GPUs. If you're familiar with the notion of a KV cache, which we'll talk about. This is what a lot of organizations initially, when they're playing with inferencing to begin with, thinks that inference looks like. I have a user, the user is querying an LLM, getting an answer, and that's it. That's correct in a POC environment usually. In a production environment, this is closer to reality. You have multiple components, LLM routers, tens or thousands of GPUs and GPU servers, multiple vector databases, graph databases, reasoning environments, right? So it's a very production-grade inference environments have a lot of moving parts. But there are some commonalities. So there's no one-size-fits-all. There's no one inference environment that can accept all of your inference requirements. So video search and summarization inference environment is not identical to a physical intelligence environment, that is not identical to a chatbot or to a risk assessment inference environment. However, there are some commonalities. For example, the importance of latency. The lower the latency of the environment, obviously, the better across all of your inference workloads. If I'm now chatting with a smart city environment and I'm asking for suspicious characters, for example, if I get an answer from my vector database and from my graph database in a millisecond versus 10 seconds, again, completely different value. If I'm now looking for some data on my storage and I'm getting it in microseconds instead of milliseconds, completely different value. So latency is hugely important. There's the two macro notions of prefill and decode within GPU inferencing. Obviously, it's much more complicated than that, but in general, when you're inputting data to the LLM, when you're putting your tax documents, when you're putting an image, and now you want to start, when you're putting your code in, and now you would like to start working with it, that's called prefilling. And then when the LLM generates output, when the environment generates output, that's called decoding. Obviously, you'd like to decode as much as possible, because prefill is a necessary evil. Decoding is where you spit out tokens, where you generate value, where if you're selling these tokens, that's where you can charge for more tokens. To compound the problem, the rise of agent swarms. So we talked about agentic workloads. It's now being even compounded further, because agents are now generating more agents and controlling more agents, and each of them is reasoning and generating more tokens. So your already problematic GPU memory environment is now even at a bigger problem, right? And then obviously, how do you create these environments in a cost and efficient way? Because just throwing more GPUs, more networking, that doesn't solve it in an economical way. You need a good ROI on your inference environments. Otherwise, what's the value? And there's this paradox that as accelerators and neurotransformers, neural models are now generating more tokens per second, we would have imagined that because of that, the cost per token, if now I'm performing like 2,000 tokens per second and tomorrow 4,000, obviously the cost per token decreases. But on the other hand, we're seeing model where their context sizes increases significantly. So, and they're generating more tokens. So suddenly the cost per token decreases, but the overall cost of your tokenized environment increases because I need more tokens. So that's one paradox that we're aware of. And this is where agentic AI is actually hitting the memory limits of your infrastructure. That's a big problem. I'll also nail the point by showing this. We can see that memory capacity across GPUs is increasing, doubling every 2 years, 40 gigabyte, 80 gigabyte, 130 gigabyte in some accelerators and more. But basically doubling every 2 years, while the context sizes of models actually, in the last 2 years, it increased by 240x. So models are now requiring massive amounts of GPU memory that the GPUs don't have anymore. And then you need to be creative. Let's do tensor parallelism. Let's run across multiple GPUs. Let's create more inference servers. but that's the memory wall, where the efficacy of your GPU memory compared to what it needs to run actually decreases. So how do we create an economic environment, an inference economic environment at scale, right? We need to scale that memory wall. We need to make sure that even though we have that memory limit, we go beyond it obviously in an economical way. And this is where we introduce the augmented memory revolution. What if you could actually have an endless capacity for your GPU memory, right? If my GPU has 80 gigabyte or 130 gigabyte, but now I need terabytes or petabytes of tokens, what if I could have that while still not constantly recalculating my KV cache, while still not taking my data and recreating my data? Essentially, that's the notion of a token warehouse, because if I already pre-filled data and I created tokens, I created KV cache structured, and now because I'm limited in memory, instead of deleting that, I go and I offload that to my augmented memory environment, then essentially that would allow me to pre-fill once and decode forever. Because every piece of data, my tax documents, my pictures, my code, would always be available for the GPUs, even though they're not strictly on the GPU memory. But instead of recalculating it, the GPU would just load it. So this is something that has been tried, by the way, in the past with DRAM, which is very local to the GPU server, with local NVMEs that are still available for the GPU servers, and also with shared storage, basic shared storage or high performance even shared storage that just couldn't handle it, wasn't fast enough. Basically, recalculating was more efficient than loading. So we had that theory at Weka, obviously, and what we did is we tested it in a production environment. We took 8 GPU servers and we calculated a real engineering development use case on it. We ran it, and we saw that with treating Weka as an augmented memory to these 8 GPU servers, we could generate 4.2x more tokens. So developers that were working on it would get 4.2x more tokens. Just to put it in perspective, imagine that our 64 GPU memory environment could behave like 256 GPUs, right? How much does a GPU cost? So there's value here. So to summarize, what does it take to win in a scale-out production-grade inference environment, which the majority of the organizations are now going to? Build a cost-effective, performant token warehouse. So again, pre-fill once, decode forever, don't throw all tokens. Generate more tokens by increasing KV cache hit rate. So by doing that, you can just generate more tokens. By the way, obviously it's more economic, and also your user experience increases. So if I'm a code developer and I'm working on your environment and you're using this, you're actually getting better feedback, better time to first token, better token interval, right? All of these nice measures that satisfaction is measured by. Having said that, what we did is, obviously, we created this environment, but it's more than that, because inferencing is not just about performance. It's not just about how many tokens per second, but it's also how can I make it, how can I create this inference environment in a simple fashion? How can I do it in a secure way? We're working with a lot of GPU clouds where multi-tenancy is a must. How can you do it in a way that your tenants can infer securely and separately? How do you do it? How do you create model repositories where your agentic workloads can just load multiple models without copying the models between the different GPUs and local NVMEs? So that's what it takes to win. And obviously, to summarize, profitable AI requires overcoming the memory wall, simply because you'll get better outcomes and it will be more cost effective. And obviously, if you'd like to learn more, please reach out. I'll stand here so you can take a picture of it. Thank you.